Hey y'all, Dr. Powers here. We're going to look at part 2 of the tutorial that I went through I went through the first part in the previous video. So in the previous one we created a population called memory experiment, and in this population we were simulating undergraduates taking part in a psychology experiment. Now, we had 3 treatment groups, and we had a response variable called score, which was dependent only on the treatment group, which was categorical. What I want to do now is build a linear dependency, which is to say I want to create a linear model for the response variable. So rather than just having it have like kind of discrete dependency, which is to say a different distribution for each of those 3 treatments, it'll be dependent on both treatment and on the GPA. Presumably, people with a higher GPA are going to do better in the memory experiment. Let's just suppose that's true. All right, so I want to talk through kind of the logic behind this. These points one by one before we build this. Now, memory scores on the test are going to range from 0 to 10, and we're going to take it that, like, let's say people with the average GPA are going to get an average score of 5. So the average or mean GPA from that distribution is 3.25 roughly. And so what I'm going to say then is I would like, ideally, for people with a GPA of 3.25, their average score would be a 5 for the memory experiment. This is for the control group. Furthermore, I'm going to ideally would like, since GPA can range from 1 to 4, I'll say for every 1 point of GPA, we would have an expected effect or an average effect on the memory score of 2. So like if you're comparing people who have 2.25 to 3.25, their average scores are going to be different by 2. And so the way we'd build that in the model would look like this now. Since this is what a linear model would look like. Y, our response variable, which is memory score, is equal to the intercept, which we'll talk about in a second, plus 2 times their GPA. This is allow us to have every 1 point of GPA will affect the memory score by 2. And then plus epsilon, and remember epsilon is some randomness that we add on at the end. Now we want to think about this intercept. Now I said I want the average score of 3.2, memory score to be 5 for individuals with a 3.25 GPA. If you take 3.25 and plug it in for GPA, what you're going to get is 6.5. That's 2 times 3.25. And so if I wanted that to be the response scores to be centered at 5, I want to subtract 1.5. That's going to be my intercept. So my constant that I'm adding to all the scores is going to be, it's negative 1.5 plus 2 times GPA plus some randomness. Now this allows us to model a linear relationship between GPA and the score on the memory test. Now we'll talk about, like I said, we'll talk about epsilon in a bit. Okay, but I want to have an effect for the treatment groups. For the old, I want to have the average score be about 0.5 less, and for the intelligent group, plus 1 more. And so these are going to be handled with these indicator variables. So this, you can see this minus 0.5 for treatment old. If treatment is old, then I'll be subtracting 0.5. If the treatment is intelligent, I'll be instead adding 1. Only one of these 2 effects is going to be in place, actually, or neither of them for the control group. So this linear expression is my linear model I'm going to use. The last bit is the epsilon. And I was thinking that for memory scores to range plus or minus roughly 3 points from the average, that's about 2 standard deviations. So I'll set the standard deviation to be 1.5. That is what I would do. So that's all the pieces. We've planned out the linear model, and now we want to build it. So let's go over to stat powers, and I'm going to show you how we open the, we can either go to the short URL that you have shared and use your key, or if you've saved the file, open that file. So I've opened the file, I choose the file. I didn't show you all the files on my computer, but you just go to it, choose it, and then it's going to open it up. You have access to all of the pieces. Now, I'm going to, the variables don't change. The variable dependencies will have a slight change because now the score variable will be dependent on treatment and a GPA. So let's check that off. And now we're going to move on to the variable details. All we're going to change is the score variable. Now it has been a discrete dependency. However, we're going to change that now. We're going to change it to a generalized linear model. The linear model has a certain syntax that it'll use. And it's basically going to mimic the linear model that we have already said we're going to use, starting with the intercept, which is -1.5. That's straightforward. Next is the GPA term, which we said we'd use 2 times GPA. Now you notice that GPA is going to be encoded as V3, or variable 3, V3. So I'm going to say plus 2 V3. That's going to, whatever the value of V3 is, it's going to be multiplied by 2. We want to subtract 0.5 for when the treatment is old. So I say minus 0.5 time, and then that's going to be when V2 equals 2. So that is the syntax you use to have the condition of old. And I'm going to have a +1 when V2, the treatment, is intelligent. So that's when it's 3. So I'm going to say plus 1 V2 equals 3. That's how you put in these two, the effect from this categorical variable. And the last bit is the randomness, which is going to be the last term, which Z symbolizes. I said we said we want a standard deviation of 1.5, and so I say plus 1.5 Z. Now Z is going to be a standard normal random variable, which is to say a mean of 0 and a standard deviation of 1. If I want that standard deviation to be 1.5, just multiply the value by 1.5 and that'll scale it appropriately. That's it. Now, when you click out of this input, it's going to show you a formatted linear model, and it should look like this. So you can see each of the terms is separate, is circled. The continuous or numerical variables are in this kind of teal color, or that's like, what would you call that? Yeah, turquoise. And then in this greenish blue, you have your categorical indicator variables. I have a -5 for V2 equals 2 and a +1 for V2 equals 3. My error term is the Z, 1.5. Everything looks fantastic. Let's just sample and test it out. Boom, sample looks good. I was able to get some sample data. I'm happy with this, so we can go ahead and save it, share it, and do all that good stuff. That's how you build a linear model. It takes a little bit of planning. It's not as easy as what we did before, but with a little, and you can look at the values. Now, at this point, you know how to, analyze some of these variables. You can see whether the distribution is what you want it to look like. You can tweak these a little bit if you need to until it looks right. I tweaked it a little bit before I posted the tutorial because the standard deviation was a little bit too much. So anyway, that's going to be your guide for building a linear model, and that's it for this video. Nice and short. Okay, bye.